You stand under a dark sky, and the stars look like random glitter. Hidden in that sparkle is something more personal. A small neighborhood around our Sunday. Within a few steps on the galactic scale, there are nearby suns you will never see. From the ground, space feels empty, but it is not. It is thinly populated and ordered. It is our cosmic address. Tonight, we are going to map that hidden district and meet the stars next door. If you enjoy exploring the universe like this, remember to like the video and subscribe so we can keep flying together. Astronomers give this neighborhood a simple definition. Everything within roughly 16 light-years of the Sunday. Put a glowing bubble around our star that wide and you capture a small cluster of other suns, brown dwarfs, and probably hundreds of planets. It sounds generous until you remember that 1 light-year is the distance light travels in a year, about 10 trillion kilometers. 16 of those stacked together still form only a tiny patch in a galaxy 100,000 light-years across. On a city map, this would not even be a street, more like a single block on the edge of town. Inside that block are around 50 separate star systems containing roughly 60 or so individual stars and brown dwarfs. Some of them you already know by name, even if you do not realize they are neighbors. Sirius, the brightest star in our night sky, lives here. So does Proxima Centauri, the closest star after the Sun, so faint you need a telescope to see it. Alpha Centauri A and B, a famous double star that often appears in science fiction, are part of the same family group. Barnard's star, Wolf 359, Ross 128, Gliese 581, and others are scattered through this bubble like dim house lights seen from far away across a field. The strange thing is how empty that bubble still is. If you took the Sun and shrank it to the size of a tennis ball, the nearest star would be another ball placed several thousand kilometers away. Most of the space in between would be pure darkness and dust. Our local neighborhood has more than 60 stars, yet almost all of the volume inside that 16 light-year sphere contains nothing but very thin gas and the occasional speck of rock or ice. Calling it a neighborhood is almost a joke, but compared with the deep void beyond, this is as crowded as it gets. What makes this patch of space exciting is not just the stars, but the worlds that go with them. With each new telescope survey, the list of nearby exoplanets grows longer. We have found a roughly Earth-sized world hugging Proxima Centauri in a brutally close orbit. We have evidence for a cold super-Earth around Barnard's star, a promising world in the possible habitable zone of Ross 128, giant planets around Epsilon Eridani, and candidate worlds circling dim red dwarfs with names that sound like license plates. Most of these planets are still only numbers in a database, yet even numbers can hint at oceans, ice caps, storms, and maybe something breathing under an alien sky. Our instruments are the only reason we can say any of this. To the human eye, almost none of these stars look special. Many are so dim they do not appear at all. We infer their presence from tiny wobbles in their motion, or from the faint dip in starlight when a planet crosses in front of them. Over time, those repeated measurements turn into orbits, masses, and hints about temperature and atmosphere. From a pile of gentle flickers and detector pixels, we build a three-dimensional map of the space around us. So when we talk about an epic journey through the local stars, we are not imagining a neat two-dimensional map like the one on a subway wall. We are talking about a messy three-dimensional cloud of suns, some near the plane of the Milky Way, some above or below, all drifting slowly in different directions. Every star is moving. The pattern of neighbors you see now will not be the same in a few million years. Barnard's star is already racing toward us. Others are sliding away. Our neighborhood is more like a slow-motion swarm than a fixed block of houses. Yet you have to start somewhere. And for us, everything begins with the star that raised us. The sun is not just one point on this map. It is the reference line, the origin, the measuring stick, and the only star we have ever visited with spacecraft. Every distance in this tour will be counted outward from that single light. Every comparison we make about size, temperature, brightness, and habitability will lean on what we know about home. Before we can truly appreciate our neighbors, we need to understand the engine in our own front yard. So next, we will fall inward, back toward that familiar blinding disk, and look under its surface. We will turn the sun from a flat circle in the sky into a layered machine made of plasma, gravity, and time. Because once you understand how an ordinary star like the sun actually works, every other point of light we meet in this journey stops being a mystery and starts feeling like a variation on a theme. And that is when the neighborhood really comes alive. To really understand our neighborhood, we have to start with the one star that does not feel like a star at all. The sun is so bright, so close, and so ordinary in our daily lives that it becomes background noise. Yet it is the reference point for everything else. Every temperature we quote, every distance between planets, every idea we have about what a normal star is supposed to be, comes from this one blinding ball of plasma we orbit every year. Before we drift outward to faint red dwarfs and exotic systems, we need to look straight into the engine that made us possible. On paper, the sun is not far. The average distance between Earth and the sun is about 149.6 million kilometers. That sounds like a phone number more than a place. So we translate. Imagine you could drive a car straight, up into space at highway speed, 100 kilometers per hour, never stopping, never slowing, never changing lanes. You would still sit behind that steering wheel for roughly 170 years before you touch the Sunday. Put the same route under a modern passenger jet flying at 900 kilometers per hour, and the trip shrinks, but only to about 19 years one way. Suddenly, the bright disk in the sky feels very far. Astronomers got tired of repeating that long distance, so they turned it into a unit. They called it 1 astronomical unit, often shortened to 1 AU. It is the basic ruler we use to describe the layout of our solar system. Mars orbits at about 1.5 astronomical units from the Sunday. Jupiter cruises around at a bit more than 5 astronomical units. Pluto, out near the frozen edge, takes a wide path at roughly 39 astronomical units. Instead of juggling billions of kilometers, we measure every orbit as a multiple of this one baseline span of space between us and our star. Light uses a different ruler. It travels through vacuum at nearly 300,000 kilometers per second. Even moving that fast, light from the sun takes just over 8 minutes to reach Earth. About 8 minutes and 20 seconds. When you step outside and feel warmth on your face, you are not feeling what the sun is doing right now. You are feeling what it did 8 minutes ago. If the sun were to somehow switch off this instant, its light would keep streaming toward us for more than 8 minutes before the sky began to change. For that short time, the entire solar system would be living in the afterglow of a star that no longer exists. Beneath that calm glow is a machine. At the center of the sun lies the core, a region where temperature and pressure reach extremes that we can barely describe. You can picture it as the engine block of a car, except it is made of plasma, not metal, and it runs on crushed atoms instead of fuel tanks. In this core, hydrogen nuclei are squeezed so tightly that they fuse together to form helium. This process, nuclear fusion, releases energy because a tiny bit of mass is converted into pure energy every time it happens. Each second, the sun fuses around 600 million tons of hydrogen. Roughly 4 million tons of that mass become energy in the form of light and heat. That is what eventually warms your skin. The energy does not rush straight out. Above the core is the radiative zone, a thick shell where photons bounce from particle to particle like someone trying to push through a packed concert crowd. Each scattering is tiny, but the journey is long. A single packet of energy can take thousands to millions of years to work its way through this region. By the time it leaves the radiative zone, the energy released by a fusion reaction in the core has been absorbed and re-emitted so many times that its original identity is completely scrambled. Next comes the convective zone. Here, the plasma behaves more like the water in a pot of soup on a stove. Hot material from deeper layers rises upward, cools as it loses energy, then sinks back down to be heated again. These giant rolling cells churn constantly, carrying heat toward the surface. This motion drives much of the sun's visible texture including granulation patterns and larger flows that wrap around the star. The first layer we can actually see is the photosphere, the apparent surface of the Sunday. It is only a few hundred kilometers thick and has a temperature of about 5,500 degrees Celsius. When you look at the sun through a safe filter, that glowing disk is the photosphere. Above it lies the chromosphere, a thinner, more tenuous layer that becomes visible during solar eclipses as a faint reddish rim. Beyond that is the corona, the outer atmosphere of the sun, stretching millions of kilometers into space. The corona is one of the most puzzling parts of the Sunday. While the photosphere sits at thousands of degrees, the corona jumps to temperatures of 1 million degrees Celsius or more. It is like standing next to a campfire and discovering that the air meters above the flames is hotter than the fire itself. Magnetic fields seem to play a key role, twisting and snapping, funneling energy upward, but the exact processes are still an active area of research. Our home star still keeps a few secrets. What we casually call sunlight is only one small slice of what the sun emits. The star pours out energy across the entire electromagnetic spectrum. There is the visible light that lets you read a page, ultraviolet radiation that can burn skin and drive chemical reactions in the upper atmosphere, infrared light that you feel as warmth, radio waves that ripple through space, X-rays that flare during violent outbursts. Alongside all of this, the sun blows a constant wind, a stream of charged particles called the solar wind, flowing outward in all directions. Sometimes the sun loses its temper. Magnetic fields on its surface twist into knots until they snap. When that happens, the star can release a solar flare, a sudden surge of radiation, or a coronal mass ejection, an enormous cloud of plasma hurled into space. When these storms reach Earth, they can trigger auroras, shimmering curtains of light near the poles. They can also disturb satellites, disrupt radio communication, and in extreme cases put stress on power grids. We live inside the weather system of a star, and our technology has to learn to cope with its moods. Chemically, the sun is simple, yet telling. About 74% of its mass is hydrogen, and roughly 24% is helium. The remaining small slice, around 2%, is everything else. Elements like oxygen, carbon, nitrogen, silicon, and iron. That tiny fraction of heavier elements turned out to be crucial because it is the material from which planets, moons, asteroids, and life itself are built. Those atoms were forged in older stars that lived and died before the sun was born. Which means our star is at least a second-generation object, assembled from recycled stardust. In the language of stellar classification, the sun is a G-type main sequence star, sometimes loosely called a yellow dwarf. It is medium-sized, medium-bright, and remarkably stable. More massive stars burn through their fuel quickly and die young. Less massive stars glow faintly, but endure for trillions of years. The sun sits in the comfortable middle. It has been shining for about 4.6 billion years and is expected to keep burning steadily for roughly 5 billion more. For a species trying to build civilizations and radio telescopes, that kind of stability is priceless. The sun also dominates our system in a more literal way. It contains more than 99.8% of all the mass in the solar system. Every planet, moon, comet, and asteroid combined makes up less than a fraction of the remainder. If you could place the entire solar system on a gigantic balance scale, the sun would slam its side down while everything else barely nudged the other end. Its gravity shapes every orbit, from Mercury's tight loop to the long, slow paths of distant comets. We do not just live near the Sunday, we live inside its gravitational well. To turn this blazing object from myth into measurable science, we have sent machines toward it. NASA's Parker Solar Probe, launched in the year 2018, is flying past the sun again and again on a series of ever-tightening loops, using Venus to steal a little orbital energy each time. It dives into the outer corona to measure magnetic fields, particle streams, and waves in the solar wind from up close. Farther out, observatories like the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and the European Space Agency's Solar Orbiter watch the sun in many wavelengths, tracking flares, sunspots, loops of plasma, and polar activity. Together, they have turned our star from a blinding circle into a detailed, dynamic world. All of this matters because the sun is not special in the eyes of the galaxy. It is an average star in an average orbit, sitting in a quiet arm of a spiral galaxy. Yet for us, it is everything. It is our first data point, the template against which we compare every other star. When we say a red dwarf is cooler, or a blue giant is hotter, or a white dwarf is denser, we are always really saying, compared with the Sunday. Now that we have peeled back its layers and seen how this ordinary star breathes, burns, and storms, we are ready to look outward again. The next lights we visit will be dimmer, cooler, and far more violent in their own way. We will take what we have learned here and use it as a guide as we leave the sun behind and set our course for the first true neighbor in the dark, Proxima Centauri. Leaving the sun feels like stepping off a brightly lit porch into a dark field. The farther we drift, the smaller our star becomes, until it is just one point of light among many. Ahead of us in that darkness waits our first real neighbor, a star you have never seen with your own eyes, even on the clearest night. It is faint, red, and easily overlooked, yet it is the closest star beyond the Sunday. This is Proxima Centauri, our first stop in the sea between suns. On a map, Proxima Centauri looks almost close. It sits at a distance of about 4.24 light-years. In the careful language of astronomy, that counts as next door. Translate that into everyday units, and the illusion of closeness vanishes. 1 light-year is nearly 10 trillion kilometers. Multiply that by a little more than 4, and you get a distance of over 40 trillion kilometers. At the speed of Voyager 1, the fastest spacecraft humanity has ever launched into deep space, the trip would take more than 73,000 years. That is longer than all of recorded human history. Despite being our nearest neighbor, Proxima is tiny. It has about 1/8 the mass of the Sun, and a diameter only a bit larger than Jupiter, roughly 1.5 times that planet's size. Its surface temperature is around 3,000 degrees Celsius, almost half that of the Sunday. This cooler surface gives it a deep red glow, which is why it is called a red dwarf. In terms of power, it is incredibly faint, radiating less than a fraction of a percent of the Sun's energy output. If you could swap our star for Proxima without moving Earth, our planet would plunge into a permanent deep freeze. The midday sky would be almost black. Yet for any worlds that hug Proxima itself, the story is different. Because the star is so dim, its habitable zone, the region where temperatures could allow liquid water to exist, lies very close in. Imagine a narrow ring tucked almost up against the star's surface. Any planet that wants to be warm enough for oceans has to orbit deep inside that ring. That means a short year, a tight orbit, and a world that likely always shows the same face to its star. One hemisphere locked in daylight, the other in endless night. Proxima may be small and faint, but it is not gentle. It is what astronomers call a flare star. Magnetic fields on and above its surface twist and knot until they snap, unleashing enormous bursts of radiation and streams of charged particles. Some of these flares have been observed to be dozens of times more energetic than anything our sun has produced in modern history. For any nearby planet, these storms are not just pretty lights in the sky. They are threats that can strip away atmospheres, sterilize surfaces, and pound any unprotected life with hard radiation. In spite of those hazards, Proxima Centauri shot to fame in the year 2016, when astronomers announced the discovery of a planet in orbit around it. The work came out of an observing campaign with a poetic name, Pale Red Dot, a nod to Proxima's color and to our own pale blue home. Instead of trying to see the planet directly, the team used a method called the radial velocity technique. They watched Proxima's light very carefully, looking for tiny shifts toward red or toward blue as the star moved back and forth along our line of sight under the gravitational tug of an unseen companion. Over many years of data, a rhythm emerged. Proxima was wobbling on a cycle of about 11.2 days. That regular tug could only be explained by a planet. From the size of the wobble and the known mass of the star, the team estimated that the world doing the pulling was at least slightly heavier than Earth, perhaps around 1.1 to 1.3 times its mass. They named it Proxima Centauri b. It orbits at a distance of roughly 7.5 million kilometers from the star, far closer than Mercury is to the Sunday. Because Proxima is so dim, that tight orbit actually places Proxima b inside the star's habitable zone. In terms of raw energy received, the planet bathes in a level of starlight not wildly different from what Earth receives. On paper, this sounds promising. A rocky world, close by in cosmic terms, sitting in the zone where liquid water could exist. It is easy to see why Proxima b quickly made headlines as a candidate for a potentially habitable planet. Then you remember the flares. A planet that close to such an active star lives under constant bombardment. Powerful bursts of ultraviolet and X-ray radiation can tear apart molecules in an atmosphere, allowing lighter gases to escape into space. Repeated over hundreds of millions of years, that process can strip a world nearly bare. Without an atmosphere, there is no shield against radiation, no stable climate, and no way for liquid water to remain on the surface. Some scientists have suggested that a strong magnetic field could help a planet like Proxima b hang on to its air, deflecting charged particles the way Earth's magnetic field does. Others are more skeptical. At this distance, we have almost no direct information. We do not have pictures of the planet, only numbers. Proxima does not host just one possible world. Further from the star lies Proxima c, a more massive planet that may be several times the mass of Earth. It probably resembles a mini Neptune, a cold world with a thick envelope of gas or ice, circling far outside the habitable zone. Closer in, there are hints of an even smaller planet, Proxima d, perhaps a quarter the mass of Earth on an ultra-tight orbit. That inner signal is still debated, and may yet turn out to be a ghost in the data. The system seems busy, but our tools are only just good enough to tease out its structure. So here we are, at the closest star beyond the Sun, staring at a world that is both tantalizing and hostile. Proxima Centauri b sits in the right place for water, yet under the wrong kind of star. It is a planet that almost feels designed to test our optimism. Is habitability just a matter of distance, or do the moods of a star matter far more than that simple ring called the habitable zone suggests? We do not know yet. What we do know is that if humanity ever finds a way to send probes to another star, Proxima will sit at the top of the list. Not because it is friendly, but because it is first. In the next part of our journey, we will look at the bold ideas that try to bridge the 40 trillion kilometer gulf to this tiny red ember, and then we will widen our view to the brighter pair of suns that share its larger family, Alpha Centauri A and B. Standing next to Proxima Centauri in your imagination, one fact hits harder than any flare. We have no way to get here. Not really. Our fastest machines would take longer than civilizations usually last. Voyager 1 has been racing outward since the 1970s, and after nearly 50 years it has covered less than a tenth of a light year. At that pace, a journey to Proxima would stretch across more than 73,000 years. If you launched it when humans were painting caves, it would only now be arriving. To cross that gulf within a single lifetime, you need something completely different. Rockets that push hot gas out the back will not be enough. You need a ship that barely counts as a ship, and an engine that sits back home and pushes from afar. That is the idea behind one of the boldest concepts ever put on the table for interstellar travel, a project called Breakthrough Starshot. The idea sounds like science fiction written on a whiteboard. Instead of sending one huge craft, you build a swarm of tiny probes, no bigger than a coin, and only a few grams in mass. Each probe carries a chip-sized brain, miniature cameras, and tiny instruments. On its back is a sail, a sheet of ultra-thin material, maybe 4 meters across, that weighs almost nothing. None of them carry fuel. They do not fire engines. They simply ride on light. Back on Earth, or perhaps on the high plateau of a future observatory, you build a phased array of powerful lasers. When you want to launch, you point the beams at one of these sails and fire. Light carries momentum. On human scales, that push is tiny. On the scale of a feather light sail in vacuum, the push can be enormous. For a few minutes, the sail is hammered by light, accelerating harder than any human could survive. If the technology works, each probe could be flung up to a significant fraction of light speed, perhaps 1/5 of that cosmic speed limit. At that pace, a journey that once took tens of millennia would shrink to a human span. Probes launched toward Proxima Centauri could cross the 40 trillion kilometer gap in just over 20 years. They would not slow down. There is no easy way to do that yet. They would zip through the Proxima system in a brief flyby, snapping pictures, tasting starlight, sampling plasma, then spending the rest of forever gliding into deeper space. Long after the launch, lasers are silent. A faint radio whisper from that flyby would arrive back at Earth. For the first time, we would have direct images of a planet around another star, not an artist impression, but real alien weather frozen in a pixel grid. On paper, many things can go wrong. Dust grains hitting at a fraction of light speed can punch holes in a tiny sail. The aiming must be precise enough that, after 20 years of travel, a probe passes through a narrow target zone near a dim red star. The returning signal would be incredibly faint. And of course, the laser array itself demands engineering on a scale we have never attempted. Yet the concept exists, funded, studied, argued over. It is not a ready spacecraft. It is a sketch of what might be possible if we decide that reaching another star is worth generations of work. If we ever pull it off, Proxima will not be just a single dot to aim at. It belongs to a larger family. Drift a little way out from this red dwarf, only a fraction of a light year on the local scale, and 2 brighter stars enter the scene. They are Alpha Centauri A and Alpha Centauri B, shining with a warm, steady light, not so different from the Sunday. Together with Proxima, they form a gravitationally bound triple system, a kind of stellar family drifting through the galaxy as one. From far away, Alpha Centauri first betrayed itself as a single bright star. Early observers saw just one point of light and gave it the name Alpha in its constellation because it was simply the brightest. Only later did telescopes reveal that this point was 2 stars so close together that the human eye merges them. Alpha Centauri A and Alpha Centauri B orbit one another in a long, looping dance that takes almost 80 years to complete. Proxima moves much farther out, on a slow, wide path that likely takes hundreds of thousands of years to circle the pair. This triple system has been haunting our stories for decades. Long before Proxima b was discovered, Alpha Centauri was a favorite setting for science fiction. It appeared on mission patches in novels, in video games, in films. Writers placed alien civilizations here, imagined human colonies, or staged first contact. They chose this star system for a simple reason. It is close enough to feel reachable, and its main stars are similar enough to our sun that life feels plausible. When people picture a twin sunset sky, with 2 suns hanging over alien mountains, they are often imagining some version of Alpha Centauri A and B. Now that Proxima has entered the picture with its risky little planet, the system feels even richer. A future fleet of light sail probes aimed at Proxima might not resolve the bright pair in detail, but the knowledge that an entire multi-star system sits just beyond our first target gives the journey a new flavor. Our first true foothold beyond the solar system would not be a single lonely sun. It would be a complex of 3 stars, a tiny island of multiple skies. So when we talk about sending chips to Proxima, we are really talking about sending them to the Alpha Centauri family as a whole. It is our nearest cluster of suns, our first realistic destination on the map of the galaxy. If we ever manage to look back at our own star from that vantage point, the sun will appear as just another pale dot in a crowded band of light, and our entire history will be compressed into a single point of origin. For now, that journey exists only in simulations and dreams. But the map is real. The family is real. And the next step in our tour is to leave Proxima behind for a moment and move in closer to those bright siblings, Alpha Centauri A and B, to see just how similar they are to the star that raised us, and how they differ in ways that might shape any worlds that circle them. From the vantage point of Proxima, the galaxy is a field of dim sparks, yet just a short hop away, in cosmic terms, two brighter fires dominate the scene. These are Alpha Centauri A and Alpha Centauri B, a pair of suns so familiar and so close that they feel like the natural sequel to our own. Seen from Earth with the naked eye, they blur into a single bright point in the southern sky, one of the brightest stars you can see. Through a telescope they separate, two golden lights holding each other in a slow, precise dance. Humans have been watching this light for centuries. In the early days of star catalogs, astronomer Johann Bayer listed it as Alpha in the constellation Centaurus because it shone brighter than the rest. For a long time, it was treated as a single star. Only as telescopes improved did observers notice that the point could split in two. Careful viewing revealed that this was a binary system, with each star looping around the other. Later still, astronomers like Thomas Henderson and Manuel John Johnson measured its tiny apparent shift in the sky as Earth orbited the Sunday. This effect, called parallax, finally revealed its distance. The result was astonishing. This was not just another bright star. It was our nearest luminous neighbor, only a little more than 4 light-years away. Meet the stars themselves. Alpha Centauri A is the larger and brighter of the pair. It has roughly 10% more mass than the Sun and shines with about 1.5 times the Sun's luminosity. Its surface temperature is around 5,800 degrees Celsius, only a little hotter than our own star. In spectral terms, it is a G2-type main sequence star, which is a fancy way of saying it is almost a solar twin. If you swap the Sun for Alpha Centauri A without moving Earth, our planet would still orbit in the habitable zone. The seasons might shift a bit, the sky might seem a touch brighter, but life could likely go on. Alpha Centauri B is the quieter sibling. It has about 90% of the Sun's mass and roughly half the Sun's brightness. Its surface temperature sits around 5,300 degrees Celsius, a bit cooler than both the Sun and Alpha Centauri A. That gives it a more orange tint, so it is classified as a K-type orange dwarf. Stars like this burn more slowly and live longer than stars like our Sunday. They tend to be somewhat calmer as well, which makes them appealing targets when astronomers daydream about long-lived planetary systems where life might have time to emerge and evolve. The two stars are bound together in a long, elegant orbit that takes almost 80 years to complete. Their path is not a perfect circle. It is stretched into an ellipse. At their closest approach, the distance between them is about 11 times the distance between Earth and the Sunday. At their farthest, that separation stretches to roughly 35 times the Earth-Sun distance. Even at the tightest part of the orbit, the two stars are far enough apart that each can host its own set of planets without constant gravitational disruption from the other. Imagine living in such a system. From a planet circling Alpha Centauri A, the second star would shine in the sky far brighter than our moon, a permanent companion light. For decades, astronomers have hunted for exactly those planets. The stakes feel high. If there are Earth-like worlds around stars this close and this sun-like, they would instantly jump to the top of every target list. In 2012, a team announced what looked like a breakthrough. They claim to have detected a small rocky planet around Alpha Centauri b, orbiting extremely close with a year only a few days long. That world would be too hot for life as we know it, but its mere existence would be proof that planets form easily here. Then came the hard part. As more data poured in and more eyes examined the numbers, doubts grew. The signal was faint and tangled with noise from the star itself. Later analyses suggested that the supposed planet, often called Alpha Centauri b flap, might simply be an artifact of the way the data had been processed. For now it remains unconfirmed, a lesson in how tricky it is to tug reliable planets out of tiny stellar wobbles. The story did not end there. In 2021, another team, using a powerful instrument on the Very Large Telescope in Chile, reported evidence for a different kind of planet, this time around Alpha Centauri A. Instead of looking for wobbles, they used infrared imaging, trying to see the faint glow of a planet's heat near the star. They found a candidate object roughly as far from Alpha Centauri A as Neptune is from the Sun, likely a gas giant or icy giant if it is real. Once again, the detection is tentative. It needs confirmation, but it hints that this system may not be empty. It may have a full architecture of worlds still hidden in the glare. Future observatories are being designed with systems like this in mind. Space telescopes with coronagraphs or star shades could block out the blinding light of Alpha Centauri A and B, letting the glow of small rocky planets pop into view. If any such worlds sit in the habitable zones of these stars, we might one day study their atmospheres, looking for patterns of gases that hint at oceans, weather, and perhaps even biology. The thought that the nearest sun-like stars could host habitable planets is one of the quiet engines driving exoplanet research forward. Even before science caught up, Alpha Centauri lived deeply in our imagination. It hosts the fictional world of Pandora in the film Avatar. It appears as a destination in games, novels, television episodes, and more. When storytellers need a plausible first stop for interstellar travel, this is where they go. Part of that is simple marketing. The name is familiar, but underneath the fiction sits real physics. Two stars, one very similar to our Sun, both close enough that a future civilization could actually travel there. Picture standing on a planet in this system. Dawn might begin with one star on the horizon, while the other hangs higher in the sky. At certain seasons, both suns would set together, painting the landscape in overlapping gold and orange light. Nights would be anything but simple. The companion star would glow bright enough to cast shadows. Proxima, the distant third member of the family, would appear as nothing more than a faint reddish point, easily missed among the background stars, unless you knew exactly where to look. Alpha Centauri A and B show us something important about our neighborhood. Not every nearby system is a lonely single star. Some are families, with complex gravitational relationships and multiple possible habitable zones. For a spacefaring species, that complexity is a gift. It offers many different types of skies in one small region of space. As we slowly back away from these twin suns, their combined light merges again into the single bright star that southern sky watchers have known for centuries. We turn toward the next target on our map, something far less flashy. Ahead lies a small, dim red dwarf that slides through the sky faster than any of these giants. It has almost no visible sparkle, yet it is racing through our neighborhood at record speed. Our next stop is Barnard's star. Leaving the bright double of Alpha Centauri behind, our next target looks almost insultingly plain. No twin sunsets, no brilliant glare, not even a sparkle to the naked eye. Yet this little ember has been famous among astronomers for more than a century. It is small, quiet, and barely visible, but it holds two records in our neighborhood. It is one of the closest solitary stars to the Sun, and it is racing across the sky faster than any other nearby star we know. This is Barnard's star, the silent sprinter. On the map, Barnard's star sits at a distance of about 5.96 light-years from Earth. That puts it just beyond the Alpha Centauri system, making it the fourth closest individual star to the Sun after Proxima and the two bright Centauri siblings. Translate that to everyday numbers, and you get roughly 56.4 trillion kilometers. Even here, in what we call the local neighborhood, the gaps between stars are harsh. At the speed of Voyager 1, a trip to Barnard's star would still take tens of thousands of years. The star itself is a red dwarf, a member of the same broad family as Proxima, but with its own personality. In spectral classification, it is an M4 type star, deep in the red category. Its surface temperature is around 3,100 degrees Celsius, almost half the Sun's. Its total light output is tiny, only about 0.04% of the Sun's luminosity. If our Sun is a bright stage lamp, Barnard's star is a dim red nightlight in the corner of a huge room. You need a good telescope and a dark sky to see it at all. Barnard's star gets its name from the American astronomer Edward Emerson Barnard, who studied it in the early 1900s. He was not the first to record its existence, but he was the one who noticed something astonishing. When he compared photographic plates taken years apart, he saw that this faint dot was shifting position on the sky much more than other stars. The background pattern of constellations is usually stable to the human eye. This one star seemed to slide slowly across it. What Barnard had discovered was extremely high proper motion. Proper motion is the apparent drift of a star across the sky once you remove the effect of Earth's orbit. Barnard's star moves by about 10.3 arcseconds per year. On paper, that sounds tiny. In practical terms, it is enormous. Over the course of a human lifetime, this little star noticeably changes its position relative to the background. In the land of stars, where everything seems frozen, Barnard's star is a sprinter. It was once the record holder for fastest known proper motion. Speed is not its only strange trait. Barnard's star is old, perhaps between 7 and 12 billion years. That is at least several billion years older than the Sunday. It has been burning quietly since before our solar system formed. During its life, entire generations of more massive stars have flared, gone supernova, and scattered their ashes into space. Meanwhile, Barnard's star has simply kept going. That is the red dwarf way. With low mass and slow fusion, a star like this uses its fuel sparingly. Where a blue giant might live only a few million years, a red dwarf can last for hundreds of billions or even trillions of years. In physical size, Barnard's star is modest. It has about 14% of the Sun's mass and roughly 20% of its diameter. If you placed it next to our star, the Sun would look like a beach ball, and Barnard's star would look like a small marble. Despite that small size, its gravity at the surface is strong because so much mass is packed into such a tight volume. It is dense and steady. Unlike some red dwarfs that throw frequent violent flares, Barnard's star seems relatively quiet by comparison. That has made it a tempting target in the search for planets. In the 1960s, Dutch astronomer Peter van de Kamp claimed to have found at least one planet there, based on tiny wobbles in the star's position. For a while, the idea of Barnard's star as a nearby planetary system captured people's imagination. Later checks, however, showed that the apparent wobble likely came from subtle changes in the telescope itself, rather than a real companion tugging on the star. Those early claimed planets were quietly withdrawn. Barnard's star went back to being a lonely ember. The story took a new turn in 2018. Using extremely precise radial velocity measurements from instruments like Carmenes in Spain and HARPS in Chile, a large team of astronomers reported strong evidence for a planet orbiting Barnard's star. Instead of tracking the star's position on the sky, they watched for tiny shifts in its spectrum as it moved toward and away from us along the line of sight. After collecting data over many years and from multiple observatories, they found a regular signal. Something with about 3.2 times the mass of Earth seemed to be circling the star once every 233 days. This candidate world was named Barnard's Star B. Its orbit places it at a distance of around 60 million kilometers from the star, somewhere between the orbits of Mercury and Venus if you dropped it into our system. That sounds close, but remember how faint Barnard's star is. Its habitable zone, the region where temperatures might allow liquid water, lies much closer in. At its actual distance, Barnard's star B is probably very cold. Estimates suggest an average surface temperature of roughly minus 70 degrees Celsius or lower. That is colder than Pluto, more like a frozen super-Earth than a mild ocean world. Even so, the discovery is important. Barnard's star B is one of the nearest known exoplanets to Earth. It orbits a star that has been a benchmark in stellar astronomy for generations. If it has a rocky surface and a thick atmosphere, it might hide subsurface oceans or geothermal activity beneath a global shell of ice. We cannot see that directly. Our current telescopes can only infer the planet's existence from the star's motion. Follow-up studies are still debating the exact strength of the signal, but the idea that Barnard's star really does host at least one planet has become widely accepted. Looking far into the future, Barnard's star's journey through space will bring it even closer to us. The star is not just moving sideways in our sky, it is also drifting in our direction. In roughly 10,000 years, it will reach its closest approach, about 3.8 light-years away. For a while, it will be nearer to the Sun than Proxima Centauri is today. Then it will keep going, sliding past and onward through the galaxy. Our list of closest neighbors will change. The map is not fixed. The neighborhood is a slow, shifting flow. For now, Barnard's star remains a quiet, nearby laboratory. It reminds us that the most important stars are not always the brightest. A tiny red dwarf can teach us about stellar lifetimes, planetary systems around low-mass stars, and the long-term dynamics of our local environment. If a future civilization builds true interstellar probes, this ancient sprinter will be one of the most tempting targets. A short hop beyond Alpha Centauri, a frozen world circling an old ember, a moving waypoint on the road to the wider galaxy. As we glide away from Barnard's star, its faint red glow shrinks back into the darkness. Ahead lies an even dimmer light, a star so underwhelming that you could stare right past it from Earth and never know it was there. Yet it, too, is one of our nearest neighbors and part of the most common kind of star in the Milky Way. Our next destination is Wolf 359, the ghost light of the local neighborhood. When you look up at the night sky, your eyes are biased. They only show you the show-offs, the bright stars that burn hard and loud. The quiet majority never appears. To meet one of those hidden neighbors, we have to leave even the dim glow of Barnard's star behind and head deeper into subtlety. Our next stop is a star that sits just under 8 light-years away, closer than many of the famous constellations we know by heart, yet invisible to the naked eye. This is Wolf 359, a ghost in our local sky. If you walked outside on the clearest night and stared straight at its position, you would see nothing. You could let your eyes adjust, breathe in the cool air, trace every pattern you know, and still you would miss it. Wolf 359 is that faint. It only reveals itself through telescopes and long exposure images, where it creeps into view as a tiny red ember. Yet in terms of distance, it is one of our closest stellar neighbors, a member of the inner circle. The star was cataloged in the early 20th century by German astronomer Max Wolf, a pioneer of astrophotography. He specialized in using photographic plates to capture wide fields of stars and then comparing them over time. In 1919, he noticed a faint point of light in the constellation Leo that seemed to shift its position more quickly than the background stars. He recorded it in his personal list of high-motion stars. The entry number in that list gave it the designation Wolf 359. The name is not poetic, but the object it marks has a quiet power. Like Proxima and Barnard's star, Wolf 359 is a red dwarf. In fact, even by red dwarf standards, it sits near the extreme faint end. It has only about 9% of the mass of the Sun and roughly 16% of its radius. That makes it only slightly larger than Jupiter in physical size, though far denser. Its surface temperature is around 2,800 degrees Celsius, which is cool for a star. As a result, it emits only a tiny fraction of the sun's light, less than 1/10,000th of our star's brightness. If the sun is a lighthouse, Wolf 359 is a single match struggling in a storm. Despite its faintness, the star is busy inside. Its low mass means that convection can mix material throughout its interior, allowing it to use its hydrogen fuel very efficiently. Where a star like the Sun will eventually develop a helium core, it can no longer burn. A very low-mass red dwarf can keep fusing hydrogen almost everywhere inside for an incredibly long time. Wolf 359 will not swell into a red giant in any dramatic way. It will simply keep shining, slowly and steadily, for trillions of years before it cools into a dark remnant. The universe is not yet old enough for any such black dwarfs to exist. Wolf 359 is a preview of a future that has not arrived. From Earth, its motion is fast but subtle. The star has a relatively high proper motion, meaning it slides across the backdrop of more distant stars over time. However, because it is so faint, this motion is not something you can watch with your eyes. Only precise instruments notice its creeping shift. It does not call attention to itself. There are no flashy outbursts recorded here on the scale of Proxima's wild flares. Compared with some of its red dwarf cousins, Wolf 359 appears surprisingly calm. So far, no planets have been confirmed around this star. Astronomers have looked, scanning for tiny dips in its light or minute wobbles in its motion, but nothing solid has emerged. That does not mean the system is empty. It could host small, rocky worlds too light for our current instruments to detect, or planets in orbits that are hard to probe with present techniques. Red dwarfs are tricky targets. Their faintness and small size demand long, observing campaigns and extremely stable instruments. As technology improves, Wolf 359 may yet reveal companions. For now, it remains officially alone. Quiet as it is in reality, the star has played a surprisingly dramatic role in fiction. Fans of a certain long-running space series know the name from the Battle of Wolf 359, a pivotal and devastating confrontation set near this very star. The writers chose it for a reason. It is close, real, and obscure, a perfect place to anchor a story about hidden threats. In that imagined universe, fleets are shattered, and lives are lost in the shadow of this faint red ember. In ours, it simply keeps burning, unaware of the legends we hang on its name. The deeper lesson of Wolf 359 is not about one star, but about statistics. Stars like this dominate the Milky Way. Red dwarfs make up the vast majority of stars in our galaxy, likely around 3/4 of the total population. Most of them are even fainter than this one. That means that if you could fast forward time and watch the galaxy in slow motion, the real backbone of starlight would not be the bright beacons that draw our eye. It would be these tiny, durable embers quietly holding their planets, if they have them, for spans of time that make human history look like a blink. As we drift away from Wolf 359, its glow shrinks from a small disk to a point, then to nothing. The darkness between stars closes in again. For a moment, the neighborhood feels almost empty. Then, ahead of us, something very different cuts through the black. A piercing white light, brilliant and steady, stands out from every other spark. It is the brightest star in our night sky, a system of extremes that has guided sailors, shaped myths, and taught physicists about the deaths of stars. Our next destination is Sirius, the dog star. Ahead of us in the dark, all subtlety disappears. One star punches clean through the black, sharp, and dark, brilliant in a way that almost feels artificial. This is not a quiet red ember. This is a cosmic spotlight. From almost anywhere on Earth, if the sky is clear and you are in the right hemisphere, you can step outside, look toward the constellation of the Greater Dog, and see it blazing. This is Sirius, the dog star, the brightest star in the night sky, and one of the strangest neighbors we have. From Earth, it looks like a single point of intense white-blue light. It twinkles hard, often flashing colors near the horizon as our atmosphere distorts it. For thousands of years, people thought of it as one object, a single brilliant star. Only in the last couple of centuries did we learn that Sirius is actually two stars bound together, one blazing young and powerful, the other the tiny hot corpse of a long-dead giant. They share the same patch of space, two very different fates locked into one orbit. Let us meet the bright one first. Sirius A is the star that you see with your eyes. It has roughly twice the mass of the Sun and shines with around 25 times the Sun's luminosity. Its surface temperature is close to 9,940 degrees Celsius, much hotter than our own star. That extra heat pushes its color toward a bluish white. In stellar terms, it is young, only about 240 million years old, a baby compared with the 4.6 billion-year-old Sunday. Where our star is a patient, middle-aged engine, Sirius A is a high-performance racer, burning fuel fast for a shorter, more intense life. If you could somehow stand on a planet orbiting Sirius A at a comfortable distance, the view would be overwhelming. The star would dominate the sky, casting a harsh blue-white light that creates sharp shadows even at noon. Nights would never be truly dark if any nearby objects reflected that light. The bright star's gravity and radiation would rule the system, but not alone. Nearby, there is another presence, small, fierce, and invisible to the naked eye. This is Sirius B, one of the most famous white dwarfs in the galaxy. A white dwarf is the exposed core of a star that has finished its main sequence life. Sirius B used to be larger and more massive than Sirius A. That extra mass meant it burned through its fuel quickly. It swelled into a red giant, shed its outer layers into space, and then collapsed inward. What remains now is a sphere of carbon and oxygen with a mass similar to the Sun squeezed into a size comparable to Earth. The surface temperature of Sirius B is around 25,000 degrees Celsius, far hotter than the surface of Sirius A, but its tiny size makes it much fainter. The physics keeping it from collapsing further is exotic. In a white dwarf, gravity pulls atoms together with incredible force, but quantum effects of electrons push back. This balance, called degeneracy pressure, holds the star up. If you could somehow scoop up 1 teaspoon of material from Sirius B, it would weigh as much as a mountain on Earth. It is a stellar corpse made of ultra-compressed matter. Sirius B was not obvious at first. Astronomers noticed that Sirius A did something odd. Its motion on the sky showed a tiny, regular wobble, as if an unseen companion were tugging on it. In the mid-1800s, observers used one of the largest refracting telescopes of the time to hunt for that hidden partner. In 1862, Alvin Clark finally spotted a faint point of light close to Sirius A. The ghost star had been found. This was the first white dwarf ever seen, opening an entirely new chapter in our understanding of how stars die. The two stars orbit each other roughly every 50 years in an elongated path. Sometimes they are closer, sometimes farther apart, but always locked in a gravitational embrace. Sirius A floods the system with light, while Sirius B spirals along like a dense coal that never quite goes out. For astrophysicists, this pair is a natural laboratory. By watching their motion, we can test theories of gravity, stellar evolution, and the behavior of ultra-dense matter. Sirius is more than physics. It is woven deeply into human culture. Ancient Egyptians watched its rising just before dawn in the summer, an event that coincided with the flooding of the Nile. To them, Sirius, which they called Sopdet, signaled renewal and fertility. Parts of their calendar were aligned with its appearance. In ancient Greece, the star was named Seirios, meaning scorching or glowing. People associated its rising with the hottest days of summer. The phrase dog days of summer grew from this link between the sun and the dog star rising together, a double heat that people once blamed for fevers and misfortune. Across the world, different cultures folded Sirius into their own stories. For some Aboriginal Australian groups, it became part of a celestial hunter. Polynesian navigators used it as a guiding marker across the Pacific Ocean. In more recent times, the star has appeared in speculative claims about ancient knowledge, especially in discussions of the Dogon people of Mali, though many of those stories are disputed or misunderstood. What matters for our journey is that one simple point of light has carried meaning for thousands of years, long before we knew about white dwarfs and orbital periods. Modern astronomy still leans on Sirius in a more practical way. Because it is bright, stable, and nearby, observatories use it as a kind of calibrator. Telescopes train on Sirius to fine-tune their optics and align their instruments. Spectrographs use its well-known light as a reference. If our cosmic neighborhood had a set of street lamps, Sirius would be one of the main bulbs used to check whether your eyes are working. As we float away from the system, both stars shrink until Sirius B vanishes into the glare of its partner, and then the pair compresses back into the single beacon we know from Earth. It will keep dominating our winter skies for a long time. Eventually, over millions of years, its motion through the galaxy will carry it to a new position. Its brightness will change, and its story will continue without us. For now, in the span of our brief history, it is a constant. Leaving Sirius behind marks a shift in tone again. We have visited the flagship lights of our sky and peered into a stellar corpse. Next, we turn our attention back to something quieter and more hopeful. A modest red dwarf, not too far away, unusually calm for its type, hosting one of the most interesting Earth-sized planets in our neighborhood. Beyond that, a whole cluster of nearby stars waits to be seen together as one community. Our journey now heads for Ross 128 and then for the wider web of the local cluster that surrounds us. After the blazing spectacle of Sirius, the next star on our path feels almost shy. No myths built around it, no ancient calendars tied to its rising. If you pointed a small backyard telescope at its place in the sky, you would see only a faint red dot. Yet among exoplanet hunters, this modest star has become one of the most intriguing neighbors we have. This is Ross 128, a quiet red dwarf about 11 light-years away, and it hosts one of the most promising Earth-sized planets in our local bubble. Ross 128 was discovered in the early 20th century by American astronomer Frank Elmore Ross, who cataloged faint nearby stars with measurable motion across the sky. In raw numbers, the star is small. It has around 17% of the Sun's mass and roughly 20% of its diameter. Its surface temperature is close to 3,000 degrees Celsius, less than half the Sun's. That makes it cool and dim, radiating only a tiny fraction of the light our star does. If you swap the Sun for Ross 128 without moving Earth, our planet would freeze into a deep global winter. What rescues Ross 128 from total obscurity is a planet. In 2017, astronomers announced the discovery of Ross 128b, a world orbiting very close to the star. Using the radial velocity method, they watched for minute shifts in the star's spectrum as it moved toward and away from us. The data showed a regular tug, something with a mass about 1.8 times that of Earth, circles Ross 128 once every 9.9 days. Because the star is so faint, that short orbit puts Ross 128b in a special place. It receives roughly the same amount of stellar energy that Earth does from the Sun. Too close and the planet would bake. Too far and it would freeze. Here, in this tight orbit, the energy level lands in the range where liquid water could exist on a rocky surface if the planet has the right atmosphere. That makes it a candidate for the so-called habitable zone. Not a guarantee of habitability, but a promising start. What makes this system especially interesting is the star's behavior. Many red dwarfs are hyperactive, throwing frequent flares and bursts of high-energy radiation. Proxima Centauri, our earlier stop, is a classic example, likely bad news for any atmosphere that tries to survive nearby. Ross 128 seems different. Observations suggest that it is relatively quiet, with far fewer violent outbursts. For a planet hugging a red dwarf, a calm host star could be the difference between an airless rock and a world with stable oceans and weather. Of course, we do not know what Ross 128b actually looks like. We have no images, only numbers. We know its minimum mass, its orbital period, and the amount of energy it receives. We can build models of possible climates, imagining everything from a tidally locked world with a band of temperate twilight to a planet with clouds and seas under a dim red sun. But until we can study its atmosphere directly, all of that remains educated speculation. Ross 128b sits at the top of many wish lists for future telescopes that could analyze starlight passing through an exoplanet's air. For a brief moment, Ross 128 also stepped into a more sensational spotlight. In 2017, astronomers using the Arecibo radio telescope picked up a strange signal while observing the star. It was brief, unusual, and apparently coming from the direction of Ross 128. Headlines flared. People wondered if we had finally overheard an alien transmission. Follow-up work showed that the signal almost certainly came from human technology, likely a satellite crossing the telescope's field of view. The mystery faded. No message from neighbors this time. But for a few days, one quiet red dwarf captured the world's imagination. Stepping back from Ross 128, it is time to widen our view. Up to this point, we have treated each star like an isolated island. In reality, all of these systems live together, inside a shared bubble of space. Everything within about 16 light-years of the Sun forms what astronomers sometimes call the local stellar neighborhood. It holds around 50 star systems and roughly 65 individual stars and brown dwarfs. It is not a cluster in the sense of a tight ball of stars. It is more like a small, sparse district in an enormous city. Within this district are other quietly important systems. There is Luton's star, also known as GJ 273, a red dwarf about 12 light-years away. It is one of the brighter red dwarfs in our sky and appears to host at least 2 planets, including a super-Earth in or near the habitable zone. There is 61 Cygni, a pair of orange K-type stars, about 11.4 light-years away, famous for being the first star whose distance was measured by parallax after the Sunday. Their steady motion earned them the nickname Flying Star, and they remain targets in the search for planets. Epsilon Eridani, only 10.5 light-years away, is another orange dwarf, younger and more active than the Sunday. It has at least one confirmed giant planet and a wide belt of dust and debris, like an exaggerated version of our Kuiper belt. It has served as the imaginary home of fictional planets in more than one science fiction story, including the birthplace of a certain pointy-eared species in some versions of popular lore. Systems like GJ 1061, with multiple super-Earths, including one in the habitable zone, round out the cast. Around almost every third red dwarf we look at, planets seem to appear. Taken together, these stars form less a random sprinkling and more a loose web of potential future destinations. If you could see space from far above the Milky Way and then zoom in on the Sun's position, the local neighborhood would look like a lumpy ball of tiny lights scattered in 3 dimensions. No clear structure, no arm or cluster, just points. Yet for a civilization just learning to step beyond its home system, those points are everything. They are the first places we will map in detail. The first we will visit with robotic probes. The first we might one day try to reach with crews. Imagine a far future in which truly interstellar travel is possible, even if only slowly. Relay stations could orbit between stars, catching and forwarding narrow beams of data. Robotic explorers might hop from system to system, updating maps, scanning atmospheres, and leaving behind instruments in quiet orbits. Perhaps some of the red dwarfs with calm light and stable planets become long-term outposts, safe harbors in a very empty sea. The local neighborhood would turn into a network of ports, connected by thin threads of traffic and communication. For now, all of that is a thought experiment. Our real tools are telescopes, spectrographs, radio dishes, and patient observation. They are enough to show us that our sun does not live alone. It sits inside a delicate, three-dimensional web of other stars, most of them small, most of them red, many with planets of their own. Ross 128 and its quiet world are not exceptions. They are part of a pattern. Once you notice that pattern, the night sky changes. The points of light stop being distant decorations and start feeling like addresses. From here, there is one more major stop on this leg of our journey. At the outer edge of what we might casually call near, around 20 light-years away, lies a system that once seemed to hold an almost perfect second Earth, then turned into a cautionary tale about how hard it is to find such worlds. It has been the target of our signals and the center of public excitement and scientific debate. Our next destination is Gliese 581, where false Earths and hard lessons wait at the boundary of our neighborhood. We have been drifting outward step by step, leaving behind the sun and its inner circle of neighbors. Now we reach the edge of what still feels like near. About 20 light-years from home sits a faint red star in the constellation, Libra, too dim to see with your eyes, yet bright enough in our imagination to have carried whole waves of hope and disappointment. This is Gliese 581, a system that once seemed to host an almost perfect second Earth and then turned into a lesson about how hard that dream really is. Like many of our quiet neighbors, Gliese 581 is a red dwarf. It has roughly 1/3 the mass of the Sun and a little more than 1/3 of its radius. Its surface temperature is a bit above 3,000 degrees Celsius, so it glows with a soft red light and emits only about 1% of the Sun's energy. On a human night sky, it never shows itself. Only telescopes reveal the tiny point that holds all the drama. Old, stable, and relatively calm, it looks like exactly the kind of star where small, rocky planets might have a long time to evolve. Over the years, astronomers have confirmed at least 4 planets here, with hints of more depending on how the data are interpreted. These worlds were found using radial velocity measurements, tracking the back and forth wobble of the star as its planets tug on it. Each new signal looked like the heartbeat of an unseen world. Some orbit close in and are likely too hot. Others circle farther out in deep cold. Taken together, they painted a picture of a busy system around a modest star. The real explosion of interest came in 2010. A team announced evidence for a new planet in this system, a world they called Gliese 581g. What made it special was its orbit. The signal suggested a planet with a mass not too different from Earth, circling right in the middle of the star's habitable zone, not skimming the inner edge, not freezing on the outer rim. It seemed to sit in the sweet spot where liquid water could exist on the surface of a rocky world. For a moment, it felt like we had found what everyone had been waiting for. An almost Earth-sized planet in a stable orbit around a quiet nearby star. Some of the discoverers nicknamed it Zarmina's World. Artists rushed to paint red-tinged skies over alien oceans. Headlines called it the most Earth-like planet ever found. People asked how long it would take to get there, as if mission planning could start next week. For a brief time, Gliese 581g became the poster child for the idea that the galaxy might be full of other Earths. Then, the harder part of science kicked in. Other teams re-examined the data. They pointed out that red dwarfs can have subtle activity patterns that mimic planet signals. They showed that when you model the star's intrinsic behavior more carefully, the supposed 11 or 30-day rhythm of a planet can fade. Some analyses reproduced the signal of Gliese 581g. Others did not. The more people looked, the more the planet seemed to hover in a kind of statistical fog. As years passed and more precise measurements came in, the consensus shifted. While a few researchers still argue for its existence, most astronomers now think that Gliese 581g is probably not real, at least not in the way it was first described. The heartbeat that looks so much like an Earth twin in the habitable zone was likely a trick of noise and stellar activity. The exciting new world dissolved back into the star's restless surface. The planets that remain are still interesting. Gliese 581c for example, is a super-Earth about 5.5 times the mass of our world, orbiting much closer to the star. It may be far too hot for life as we know it, possibly a hothouse with a dense atmosphere. Others, like Gliese 581d, have also moved in and out of favor as data have been reinterpreted. This system has become a textbook case in exoplanet detection, showing how fragile the evidence for small worlds can be, and how important it is to stay cautious, especially when we want a result to be true. Gliese 581 is not just a place we have watched. It is one of the few stars we have actively spoken to. In 2008, a project called A Message from Earth used a large radio telescope in Ukraine to beam a carefully prepared signal directly at Gliese 581. The message contained hundreds of individual notes and images from people around the world, compressed into a stream of radio waves and launched across space at light speed. It will arrive near the star in the year 2029. The odds that anyone is there to receive it are unknown and probably low. Maybe the system is lifeless. Maybe any civilization that once existed has long since vanished. Or maybe the signal will wash over a dark, quiet world with no ears to hear it. Still, the act of sending that message says something about us. We are a species that points dishes at the sky, encodes our presence into radio pulses, and aims them at faint red dots 20 light-years away on the off chance that someone is listening. It is both hopeful and a little unsettling. Standing here at the edge of our tour, surrounded by faint suns and their hidden worlds, it is a good moment to zoom out. Everything we have visited so far, from Proxima and Alpha Centauri to Barnard Star, Wolf 359, Sirius, Ross 128, and Gliese 581, lies within a bubble only about 20 light-years across. That is a sphere 40 light-years wide in total diameter. It feels enormous when you imagine crossing it with current technology. Yet compared with the Milky Way, it is a speck. Our galaxy stretches roughly 100,000 light-years from side to side. It holds something like hundreds of billions of stars. If our 20 light-year bubble were a front yard, the Milky Way would be an entire continent. We have walked only a few meters beyond our doorstep. The rest of the city, the rest of the world, remains unexplored. Still, this small sample has already changed how we see ourselves. We now know that our sun is not isolated. It lives in a sparse but real community of stars. Most of them red dwarfs, many with planets, some with worlds that sit in the soft ring where water could flow and clouds could form. Some of those worlds circle violent flaring stars. Others hug calm embers like Ross 128. A few, like the candidate planets around Alpha Centauri, sit under suns not so different from our own. We have found hints of oceans and climates in the numbers, but no clear sign of life yet. That may take decades more of telescopes, or centuries of waiting for the first interstellar probes. In the meantime, the local neighborhood does something subtler. It anchors us. It gives us a sense of place. These are the destinations we can name and map now. If humanity ever becomes a species that travels between stars, these will be the first ports, the first pit stops, the first alien skies we actually see. For the moment, our ships are made of math and imagination. We ride beams of information rather than light sails or fusion drives. Yet even that journey matters. By tracing these faint points of light, by learning their stories, by admitting our mistakes and refining our maps, we are doing the same thing our distant descendants will do with real engines and real hulls. We are exploring. So as we pull back from Gliese 581 and let the whole neighborhood shrink into a cluster of tiny sparks, we can finally look again at the Milky Way as a whole. Somewhere in one of its spiral arms, circling an average yellow star, a species that only recently learned how to split atoms is already drawing up plans to knock on the doors of other suns. We are small, but not insignificant. The stars around us are not just decorations on a dome. They are real places. They are destinations. And this little neighborhood of 50 or so systems is only the beginning of the road.